Have you ever wondered how power gets efficiently distributed from power stations to your houses or offices? It's all due to a critical process called power load flow analysis. This vital procedure ensures that electricity reaches us safely and efficiently. Imagine a river flowing from its source to the sea, taking different paths. Similarly, power load flow analysis is the study of how power flows from the power station, the source, to us, the sea. However, unlike a river, power doesn't just flow along the path of least resistance. It's carefully managed and directed to ensure every corner of our cities, every light in our homes, and every appliance in our offices is powered. This essential analysis is the behind-the-scenes hero of our modern lives, ensuring that electricity, the lifeblood of our society, is distributed efficiently and effectively. So, without further ado, let's delve into the world of power load flow analysis. Before we dive into the step-by-step explanation, let's understand the basic concepts involved in power load flow analysis. The world of power systems is vast and intricate, with numerous components working together to ensure the smooth flow of electricity from generation sites to your homes and offices. At the heart of this system is the load flow study, an essential tool used by power engineers to analyze and plan the power system. It provides a snapshot of the power system under steady-state conditions, giving valuable insights into the system's performance and highlighting any potential issues. One of the key components in this analysis is the transmission line. These are the highways of the power system, carrying electricity over long distances. They connect power plants to load centers, ensuring that electricity generated reaches its destination. Next, we have bus systems, another crucial element in power systems. These are points in the power system where power is either generated, transmitted, or distributed. They play a vital role in maintaining the balance between power generated and power consumed, ensuring the system remains stable. Now let's talk about power flow equations. These mathematical formulas derived from Kirchhoff's laws provide the relationship between the power, voltage, and current at each bus in the system. They form the backbone of load flow analysis, helping to determine the power flow in the system. So, why is all this important? Well, power load flow analysis is crucial for system planning and operation. It helps engineers understand how power flows through the system and identifies potential issues that could lead to system instability or failure. By understanding these basics, we can better appreciate the importance of this analysis in ensuring the reliable operation of power systems. Now that we've got the basics down, it's time to walk through the process of power load flow analysis. Let's take a closer look at the process of power load flow analysis and understand how it works. First, we initiate the process with the initialization of the power system model. This model is a representation of the electrical power system we're working with. It includes all the key elements: generators, transmission lines, transformers, and loads. These components are all represented by mathematical equations that describe their behavior within the system. After the model is set up, we move on to the next step, the input of data. Here we gather essential information about the system, such as the power generated and consumed, the impedance of transmission lines, and the voltage at various nodes. This data is crucial as it gives us a real-time snapshot of the system's current state. Once we have all the data, we proceed to the calculation of power flow. This is where we apply a set of algorithms to solve the mathematical model, determining the voltage, magnitude, and angle at each node in the system. Various methods are used to calculate power flow, such as the Gauss-Seidel, Newton-Raphson, and fast decoupled methods. Each has its own pros and cons, but all aim to accurately solve the power flow equations. Next, we have the iteration process. The initial calculations may not provide the exact solution, so we repeat the calculations using the newly obtained values. This iterative process continues until the changes in the voltage magnitudes and angles are negligible, meaning we've reached a convergence. Following this, we come to the load flow study. Here, we analyze the results of the power flow calculations. We look at the power losses in the transmission lines, the voltage profile of the system, and the reactive power flows. This study helps us understand how power is flowing through the system and identifies any potential issues like overloads or voltage drops. The final step is the analysis of the results. We interpret the findings from the load flow study and make informed decisions based on them. For instance, If we find that a particular transmission line is overloaded, we might need to upgrade it or reroute some of the power. If a node has a low voltage, we may need to adjust the reactive power compensation. This step-by-step process is a simplified overview of power load flow analysis. It's a complex procedure that requires a deep understanding of electrical power systems and advanced mathematical skills. But it's also a crucial tool for ensuring the reliable and efficient operation of our power grids. And that, in essence, is how power load flow analysis is carried out. So, what are the key points to remember about power load flow analysis? Well, let's recap. First, power load flow analysis is paramount in the field of electrical engineering. It helps us understand how power flows within a network, ensuring efficient energy distribution. Second, the basics of power load flow analysis involve complex numbers, matrices, and algorithms, but don't let that intimidate you. Once you grasp the basics, everything else falls into place. Next, we walk through the step-by-step process of how a power load flow analysis is conducted. From setting up the system model to calculating the power flow, we've seen how this intricate process unfolds. And lastly, we emphasize the role of this analysis in power systems. It's not just a theoretical concept, but a practical tool that engineers use daily to ensure our lights stay on. Remember, power load flow analysis is the backbone of our power systems, ensuring efficient distribution of power from the source to the load. Thank you for joining us on this enlightening journey. Stay curious, stay energized,